Hello, so I hope the last presentation this week, and we shall devote our attention to real and complex limits, continuity. Right, so what shall we consider are functions which are defined on real numbers. So we have got some subset A, which is a subset in real numbers, and the function might have values in R or it might have values in C. So of course it could have values in many other scalars, but let us restrict to those two, either R or C. And of course the subset A is a definition domain, so if it's empty set, so it's trivial, not very interesting. If A would be natural numbers, we are dealing with sequences. If A is an interval, then the function will be defined only on that interval. And the values might be complex or real, who cares? And on top of that, we shall also add the sort of not real numbers, plus and minus infinity, which means that we shall consider the real line in such a way that there is 0 here, here are the minus numbers, here are the plus numbers, and here we imagine that it just goes on and ends in a point which we will call plus infinity. And here we think it goes further and it ends at a point which we think to be the minus infinity, right? And in the previous presentation I was talking about the neighborhoods. So if we just fix a point somewhere, so a neighborhood of the point would be simply, well, I mean a delta neighborhood would be such an interval. Yes, so here I have the point in the middle, and this is plus minus delta, right, from the point. And a neighborhood of infinity means that I start somewhere and I go to the end. So that would mean that I have some big numbers, say R, and anything which is bigger than R is the neighborhood of the plus infinity, and similarly with the minus infinity. And we say that the function is having a limit in a point x0 if the point x0 is a limit point of the definition domain, right? So for example, if we deal with the case of sequences, so our A, so the big A is the natural numbers, and the only limit point of natural numbers in the sense I was just explaining is the plus infinity. So the only limit I can make with a sequence is to make the limit in infinity. If the domain A is the whole of R, so all real numbers, then I can take any number. And I can take any ugly subset A, and I have to imagine that or respect that the limits can be defined only in the limit point. So the limit point does not necessarily be part of A, right? So that's something we came to in the last presentation. And it's very easy, the definition, it follows the common sense. So we say that the limit is A if for every neighborhood of the limit value there is a sufficiently small neighborhood of our limit point x0 of the set A, such that for all elements which are close enough to x0, which means they are in A and they sit in my neighborhood, but I don't request anything for the x0 itself, that's important, then the values are already there. So if you imagine, so if I have a function, I will have some ugly subset under the real line. So this is the real line. Here I have some ugly subset A, and I have a function f which goes again into real lines, and then I fix some value here. Well, here I fix first the x0, which will be a limit point, so somewhere inside of A, so that I can approach the point inside of A. And I will say that the function has got a limit here if for every neighborhood which I fix here, so I just take this neighborhood which has got something like, say, 2 epsilon, which is bigger than 0. Then I know how close is sufficient to be to x, so that the f is really just bringing this to there, right? So I really hit the neighborhood. And that's the definition of the limit. And that's the whole miracle of mathematical analysis. So that's the only thing we have to add to say, linear algebra and other simple stuff which I'll be dealing with later in order to get through. So as I already told, the first important example is if we deal with the limits of sequences. So limits of sequences means that our domain is n, the only limit point is infinity, and we simply go to the definition, right? So it means that the limit is a if for every neighborhood of a, which could be the neighborhood of a real value a or complex value a, which would be a disk, say, or it will be, if it's infinity, so it will be the rest of real line after some big enough r. We simply have to be in the neighborhood with all the members of the sequence after this n, right? This capital N. So that's easy. If I have an interval, so I can have limit of function in all points in the interval, the interior points, right? And that's very easy. So you can see, for example, if I have a function which is everywhere 0 and in 0 x 1, then of course it has got a limit in all points, and in all points the limit will be 0. Yeah? That's important to see because you have to see that the value in the limit point I'm taking the limit in doesn't matter. So I can, in x0 equals 0, I can have value whatever I want, but it's important how the function behaves on the neighborhood of that, and there it's everywhere 0. So that's very easy. Well, we can also have one-sided limits. So you can imagine that if we have the function, well, let me just come here and draw a picture. It will be better. So if we have, say, a function, I will draw the graph of it and say it will be just at 0. That will be our limit point, and I will have a function which goes like that from this side and then jumps and goes like that here, right? So that's not very good because that wouldn't be a function. So let's have it this way. And then of course the limit, if I go from the left here, then this will be the limit value, and if I go from the right, then this will be the limit value, right? So from left it will be this limit value, from right it will be this limit value. So you see that I can have different limits from left and right, and that's the one-sided limit. And how to use the definition? Well, that's easy because you simply say that you restrict the definition domain, right? And the definition domain will be only the the interval from minus infinity to the point. And then the other will be from the point to infinity. And I have then the boundary point as the limit point there, and I can take the limit as it's defined before. So again, everything will work. There is a nice function which is called Heaviside function, we shall meet quite often, which is defined diverse ways, and it's very often met in data science, in machine learning, because you have something which would be, say, all the time 0 up to 0, then it will jump to 1/2 here, and then it goes from 1 up to infinity, right? So that's called Heaviside function. No. This is the name, Heavisides. Right, so this is, and you see that here, although the value is 1/2, no one cares. The limit from the left at 0 will be 0. The limit from the right at 0 will be 1. Right, so that's it. Right, so what about if the function goes to the complex numbers, right? So if it goes to the complex numbers, Nothing special happens because we measure the neighborhoods are given by the distance, and we know that the distance in the complex plane, the square of the distance is obtained as the square of the distances in the individual coordinates. And therefore, every limit will exist if and only if the two separate limits do exist, right? Because every such a function f from a to complex numbers can be considered as a couple of functions. So why not? So we've got simply that the limit of fx is the limit of the real part as the real part of the limit, and the limit of the imaginary part for the imaginary part of the limit. And it's just unique, right? So, and it always exists if and only if. So that's pretty easy. Right. And let's have a look at functions which will be really strange, right? So you can imagine, for example, the fourth example. There are all the examples before are easier, but this one is particularly nice. So it's a function which is having quite simple definition, right? So it's a function from R to R, and at 0 it will be 1. At irrational numbers it will be 0. And at rational numbers, so all numbers p over q, where p and q are coprime, the value of the function will be 1 over q, so I simply forget about the p. And this function has got nice shape, so you see it here. And the people call it, well, either by some names of people, that's not that interesting, but also popcorn function or raindrop function. And the funny property of that function is that it's such a wiggly thing, but actually the limit at each point x0 of R exists, and the limit at each point is a 0. So the limit is always 0. So essentially it doesn't matter where you are, it's only occasionally jumping up in the neighborhoods, but essentially it's 0, right? Which is pretty fancy. It says something about how the rational numbers are distributed in the real line. Right, and straight from the definition you have a couple of theorems which are very useful when you handle limits. So one of them is that you would like to see this, so it corresponds to the picture if I have simply something like three functions, right? So it will be like that, and now I will have one function, and then I will have another function like this, say, and then I will have some third function, which has the property that at each point the values are between the two, so they are squeezed by them. And if those two functions have of common limit in some point, then the squeezed one must have the same limit, right? So that's roughly the squeeze theorem, very useful. Right, so then, yeah, here you have a much nicer picture of the same thing as I did. And then, of course, now we come to the point that whenever you have functions on any set, but valued in scalars, so you can pointwise make the operations from the scalars. So you can add them and you can multiply them. That's exactly what is here. And what the theorem says is what happens with limits of functions under addition, under multiplication. And if the limit of one of them is not 0, then you can also divide them, right? And this works exactly the same way. You can go through the proof and imagine what the proof says for the main cases, right? A sequence with a limit, a function defined on an interval, and so on. So this is quite straightforward. So what is next there? Yeah, we should come to the infinite values, right? So the previous theorem was formulated for finite limits, but actually the proofs show that it works also for the infinite limits, but with some with some limitations, because of course, I mean, if we have things like infinity minus infinity in the two limits, we don't know where it ends. It can end anyway, right? With such two. And the same if you multiply something which has got zero limit and the other one would be plus minus infinity. Not easy to say. And similarly you can't tell much if there is a quotient of two infinities, right? So again, so these cases must be handled differently. We shall come to some methods later, but in principle, the fact that the limiting process is taking a limit respects the scalar operations. So you may add the limits or multiply the limits. It works, right? And the next proposition is very useful, rather in proofs. So it's of theoretical value than for anything else, but it's roughly speaking says that if you want to discuss how a function could behave and what would be the limit, what would be its limit, so let's say we have got a limit point here of the definition domain, and we have a function which just behaves like this and goes then further somewhere, right? And we want to see that the limit value will be this, right? And then it's equivalent to the fact that we can take a sequence of points which would converge to this, and so we have a sequence of values then here, and the limit of the original function is the value we have in mind if and only if for every chosen sequence which converges to x0, the sequence will have the very same limit, right? So this is the so-called convergence test, very useful, but only for technical reasons, right? So you perhaps won't need it very much if you would be skipping the proofs later. And now we come to the last concept we want to talk about today, and that's the continuity. So continuity means that we say that the function behaves continuously if small changes of the arguments cause small changes of the values, right? So that's the common sense understanding. How do we tell it in the language of mathematics? We simply say that f defined on definition domain A is continuous at a limit point x0 in A if and only if, so here I define the function on an interval, so it's easy because each point in the interval will be a limit point, and we say that it's continuous if the limit at the limit point equals the value in the same point. So that's very easy. So that means it's continuous in the point, and we say that it's continuous on an interval if it's continuous in each point. So again, there is a picture which shows it nicely. So it's just I choose how much I allow to deviate from the value, and then I must be able to decide how close I must be or should be, what's enough to be from the limit point in the definition domain to fit into the allowed maintenance, right? So that's it. And of course, from the previous theorem that the limiting procedures are compatible with the scalar operations, it's clear that a sum of continuous functions is again continuous, multiple is again continuous. If the limit is non-zero, then the quotient is well defined on some neighborhood. That's because if you have continuous function which is non-zero, then on some neighborhood it must be again of zero, right? So I had here a picture of a continuous function in the x0, right? So you see the value is not zero, and therefore I can I can simply say that, for example, I will allow to go up to the middle here. And from continuity, I know that being close enough ensures that I will not be below this, and therefore it will be all the time there, and therefore it will be all the time also non-zero, right? So a continuous non-zero function in a point is non-zero on the neighborhood, and therefore I can consider the quotient on the neighborhood, and this will be again continuous, right? So we can build continuous functions by the arithmetic operations, and the same is true if you compose two continuous functions, it's again continuous. And in some sense, with some care, this is all true also in the infinite limit points and infinite values. Right, so there should be a picture, isn't it? It's strange, I thought here I perhaps will have it. Yeah, here is a picture which shows it, that the composition of continuous functions must be continuous again, right? Because I made the composition, and for this neighborhood I find the small enough neighborhood here, and during I'm matching, I'm hitting the right part, and then for this I can find the right one here. And so if I compose, I will hit from this small neighborhood only things in these targets. So that's okay. And what's in between here is the topological characterization of continuity, right? And that's exactly what I had in the picture. So instead of talking about a neighborhood, I can also talk about any open subset, right? And F is continuous if and only if the inverse image of open subsets are open in A. Open sets in A are intersections of open sets in R with A, right? If the inverse of closed sets is also closed, the continuous images of compact sets are again compact, and the most important part here is that not most important, but the really useful part is that if F is continuous, then restricted to any compact set. So if you restrict the function to a compact set, then on the compact it must attain its maximum and minimum. That's pretty important and useful. So you can go through these. We shall be using it quite often, and the corollary is that the image of open intervals is always an interval, and F always takes all the values between the minimal and maximal one on a closed interval, right? Closed intervals with finite A and B are compact sets, right? So this works. And again, I mean, I don't say it's completely simple to go through, say, the technical proofs and verifications of all the things, because as standard in mathematics, we have to use only the axioms. We can't look out of the window, wave hands, and say, "Oh yeah, that sounds good. It looks okay. It's true, right?" Or to try 10,000 times with some functions in Sage and get the answer. No, you have to prove it just by concise argumentation. So it's not strictly necessary to do it right now, but it would be good to start with that sooner or later. Right, and here you see if you have limits of composite functions, then there are some special rules how to compute the limits, right? Again, you can if you compute limits of composite functions, then you can think about replacing the composition and the limiting procedure, right? So that's exactly what this theorem says. Right, so that's all I wanted to say. So I hope it wasn't too vague, or it wasn't too detailed. And as I try to convince you, I'm trying to say provide some guidelines, and it's up to you whether you prefer to hear the guidelines once you try to read through yourselves first time and then have the explanation again, or if you do it, say, in spirals, like listening a few minutes, then trying to read through, then coming back, etc. It's completely up to you, and I wish you nice rest of the week and weekend.